Hi, welcome to videos on stability analysis using Nyquist plot. So in this video we'll see the basics of Nyquist criterion. Okay, let us see the introduction of this Nyquist stability. So this is a very basic introduction to the Nyquist stability. Let us try to consider a transfer function, a open loop transfer function with a unity feedback as 10 by s plus 2, where we have the pole at minus 2 in the s plane. So with the feedback transfer function as 1. If you just make this 1 plus gfs into hfs, the transfer function reduces to this form where it is s plus 12 by s plus 2. So where you can see this is the 0 representation, this is the pole representation. The 0 of 1 plus gfs into hfs is at minus 12, whereas the pole of 1 plus gfs into 1 plus gfs into hfs happens to be at minus 2. So what we are trying to do is, so this is your open loop transfer function. You are simply making 1 plus gfs into hfs. So this will have a 0 at minus 12. This will have a pole at minus 2. Let us move on now. So let us still consider the same transfer function. Let us try to find out the characteristic equation of this, which happens to be 1 plus gfs into hfs equal to 0. Suppose, of course, we are naming it as f of s. If f of s is 1 plus gfs into hfs, and if it is equal to 0, I will end up with, for this gfs into hfs, I will end up with this as the equation. So this happens to be the characteristic equation of a system having this as the open loop transfer function. So the roots of this particular transfer function is minus 12. So what I mean to say is the roots of this transfer function having a open loop transfer function of 10 by s plus 2 is at minus 12. So we have the open loop pole at minus 2. We have the roots of the characteristic equation at minus 12. And if you consider the closed loop transfer function, that is CFS by HFS, so which is given by the expression GFS by 1 plus GFS into HFS, this reduces to this particular transfer function, which is 10 divided by s plus 12. If you can see now, the pole position is at minus 12, so you don't have a finite 0 here. So we have a pole of closed loop transfer function at minus 12. So let us try to summarize all these things. So that is GFS into HFS, just 1 plus GFS into HFS, then the characteristic equation, then the closed loop transfer function. If you can see all these, so now that's what is the summary what we have. This is an open loop transfer function. This is 1 plus GFS into HFS, which has got a pole at minus 2, a 0 at minus 12. So this open loop transfer function has got a pole at minus 2. And then we considered f of s, which is the characteristic equation, has got a root at minus 12. We have got the closed loop transfer function, which has got a closed loop pole at minus 12. So looking at all these four, so I can say that, or we can conclude that poles of GFS into HFS, that is this minus 2, is equal to poles of 1 plus GFS into HFS, which is evident here. You can see this is s plus 2 in the denominator, which is exactly same s plus 2 even for this 1 plus GFS into HFS. That is, pole of GFS into HFS is same as pole of 1 plus GFS into HFS. So this is one understanding. Next is the 0 of 1 plus GFS into HFS. That is exactly this. This one 1 plus GFS into HFS. This is 1 plus GFS into HFS, which is not equal to 0 here. This is not the characteristic equation. This is simply 1 plus GFS into HFS. See the 0 position. Here it says that 0 of 1 plus GFS into HFS, in this case it is minus 12, is equal to root of the characteristic equation, which you can see here. This is the characteristic equation. You can see root is minus 12. Here 0 of 1 plus GFS into HFS is also minus 12. So these two are same. That's what the meaning is. Next, it also says that this is equal to pole of CFS by RFS, that is closed loop pole. So this is a closed loop pole. It's again at minus 12. We just see this is minus 12, this is also minus 12, this is also minus 12. This is a 0 of 1 plus GFS into HFS. This is the root of the characteristic equation, and this is the pole of closed loop transfer function. So that's what is the meaning of this statement. 0 of 1 plus GFS into HFS is root of characteristic equation, which is equal to poles of CFS beta, that is closed loop poles. So let us move on with this concept. So let us have this in mind. Okay, let us go to this mapping of contour. So let us assume that you have a characteristic equation which is sorry, it's not characteristic equation, it is 1 plus GFS into HFS. So I have 1 plus GFS into HFS. This is not equated to 0. 1 plus GFS into HFS has got 2s plus 1. This will actually have a 0 because you don't have anything in the denominator. It actually has a 0 at minus half. You can see there is a 0 at minus half. And you can see we have written a contour which is just enclosing this 0. So there is a 0 of FFS in the S-plane which is placed at minus half, and we have written a contour which is actually enclosing this 0. What do you mean by enclosure is, when I just move along this path of this square box, so this 0 should be onto the right hand side. So I can say I'm just moving here, this is there to the right hand side. If I'm moving here, this is there to the right hand side. If I'm moving down here, this is again to the right hand side. So whatever comes to the right of it, we call it as enclosed. Whatever that comes to the left of it, we call it as not enclosed. So by this we can say this minus half 0 which is there at minus half is now enclosed by this contour, which we call it as ABCD in this particular example. Suppose if I want to map it onto a different plane, now this is S plane, I want to map it onto FFS plane, where the x and y axis, you can see now the x axis is alpha, okay, gamma here, and this is sigma, and this is j omega. Suppose if I change this x axis to u and y axis to v, so let us try to find out what is the values of u and v in terms of omega and this sigma. So this is the actual values. Now we can see this is j1. If it is j1, this is the value of this omega. You can see this is omega is actually 1. This is actually 0 here because this is on the matched axis. For a value of j1, what are the corresponding values of u plus jv? If you can see here, if you substitute the value of omega and sigma here, so since omega is equal to 0, omega is equal to 1 here, this is actually omega is equal to 1, and here you can see this sigma is equal to 0. So what you have now is, so since we have here you can see when this value of real axis is 0, so this is actually 0 now, it is 0 plus 1, so you can see the real part of that is 1, whereas omega is equal to 1, so the v value happens to be it is 2 plus 1, which is 2. Now you can see this particular point has been now mapped to 1 plus j2, so meaning this line of the contour is now mapped to, this is 1 plus j2, so this is that equivalent point. Similarly, if you consider this, okay, 1 plus j1, which is over here 1 plus j1, the corresponding position of the contour in FFS plane. So actually what we are trying to, okay, how do we get this mapping is, you substitute the value of s, that is s as 1 plus j omega. So when I say j omega, okay, now the value of omega is equal to 1 here, so that's why you have it as 2 into 1, which is this is 2, so here you have this as j2, and since the real part is at 1 point at a magnitude of 1, it is 2 into 1 plus 1, which is 3 plus j2, so this is 3 plus j2. So likewise this point is mapped to here. So likewise, suppose if you consider this point mapping onto this FFS plane, since this is 1 and j is equal to 0, so the imaginary part, this becomes 0, and since this is equal to 1, you end up with 2 plus 1, 3. So 1 is becoming 3. You can see this point is now mapped onto this. Likewise, each and every point of the contour can be mapped onto FFS plane. It will end up with a contour which is something like this. So meaning what we said is, we have written an arbitrary contour which is enclosing this 0 of f of s is resulting in one more contour on f of s plane. Now what is to observe here is, so let us try to see these definitions what we have here. So we have a definition like number of encirclements of the contour in f of s plane is, which is n, is equal to z minus b. So what does it mean is, number of encirclement of this contour on this f of s plane, how many times this will encircle the origin of the contour. Origin of this f of s plane is always equal to z minus b. So what is this z? This z is nothing but number of zeros of f of s enclosed by the contour in s plane. So in this particular example, this is a 0 which is enclosed by this contour. So in this particular example, z becomes 1. Whereas p is the definition of poles of f of s enclosed by the contour in s plane. So in this s plane, since I don't have a pole, that value of p is equal to 0. So in this particular case, n is equal to 1 minus 0, which is equal to 1. So what does this n is equal to 1 stand says? N can be either positive or negative. If n is equal to positive, it actually means it's a clockwise encirclement of the origin of f of s plane. So you are actually encircling the origin of this f of s plane once in clockwise direction. That's what is the meaning of n means. So n actually means n is actually equal to the number of equation is z minus p, where z is equal to number of zeros of f of s enclosed by the contour in s plane, and p is number of poles of f of s enclosed by the contour. In this particular case, since we have only one 0 which is enclosed by this contour, so z equal to 1, p is 0. So as per this equation, as per the observation also, we can see the origin of this f of s plane is encircled by this contour once in clockwise direction. You can see it is moving in the clockwise direction and it is encircled once. So that's what is the meaning of n is equal to plus 1. So let us move along to a different mapping of the contour. You will understand more. Let us consider this. You can see you have a different contour now, a different 0. You have a 0 at the origin. Now you have a different contour which is like this. Suppose if you write a corresponding contour onto f of s plane, it looks like this. If you can see, if you just compare the values of, if you just compare or try to find out what is the value of z, since this is a 0 of f of s which is now enclosed by this contour, so z is equal to 1. Since there is a, actually this is, let me just, okay, now there is a pole here. Since this pole is not enclosed by this contour, this is not enclosed because this is onto the left hand side. Since there is a pole, but this pole is not enclosed by this, so that's why p is equal to 0 here. Why p is equal to 0 even though you have a pole here? Because this is not coming within the right hand side of this contour. So this is there onto the left hand side of the s plane, so that's why p is equal to 0. So now n is equal to 1 minus 0. So this contour which is enclosing only 1 0 of f of s is encircling the origin of f of s plane once in clockwise direction. So that's what is the meaning of n is equal to plus 1. Let us move on to third example. Now you can see you have a 0, you have a pole that is enclosed by this contour. So both z is equal to 1, p is equal to, because both are enclosed by this contour. So naturally, the value of n is equal to 1 minus 1, which is 0. You can see the corresponding contour in f of s plane is not encircling the origin. Of course, you have a closed contour on this plane, but you can see this is certainly not encircling this origin because the zeros and poles enclosed by this contour is same. So that's why n is equal to 0 here. So let us go to next one. So this is a random contour. You can see number of zeros enclosed is 3, number of poles enclosed is 1. So as per this, it is equal to 3 minus 1, which is 2. If you can just carefully notice this center, the origin of this is encircled twice by this contour. You can see here this is encircling once, This is second time it is encircling. Likewise, n is equal to plus 2.